So one thing I was kind of just, I know it's after lunch, so I thought I'd start out with something a little bit more open-ended. So I'm from the United States. Something I found that was kind of interesting here, I'm kind of curious if you guys, depending where you're from, something that's very interesting is it seems like everything that you have switches, like plugs, lights, anything. There's always a switch for every little thing, right? If you look at the power plug, there's a switch. In the United States, they don't care about that. So I don't know, is anyone else noticing that's kind of an interesting thing for the Singapore, this Asia area? It's just, for me, it's something very interesting, so.
It's going to be the weirdest thing about going to the US.
Yeah, it's like you turn a switch and the whole light, all the lights in the house turn on. It's pretty crazy, it's a complete difference. Mic okay? All right, cool. So the good news is this is something the team has been working on for a while now, and they actually applied and filed for a patent, and they got approval to go ahead and share all this information. So towards the middle of the presentation, I'm going to be talking about what they kind of worked on, all the components of that, and of course we'll share the slides after the fact so you guys can kind of get the detailed view of how all this stuff was put together. A little bit about myself. Like I said, I was from the United States. I'm from Phoenix, Arizona. And it's probably going to be in the highest it gets there is probably in the 40, 45 degrees Celsius. So just about 100 to 110 Fahrenheit. So it's very similar, but a lot more drier. I've been doing technology for, like I said, 25 years. Started out as an Apple technician, worked on iMacs and laptops, which is a really good gig. Ended up transitioning to database engineering, did that for several years, worked on a lot of problems, saw a lot of cool things. Transitioned my way into architecture, did basically database architecture and then infrastructure architecture for some data centers we had for the financial institution I worked with. And then now I'm doing some solution architecture stuff for IBM over the last year. So a little bit about myself, but we also want to give credit to all the people that kind of worked on all this work. So their names are on here. So if you feel free, they're always open for you reaching out and asking questions. If you want, you can take a picture of the screen. If not, this will be available after if you want to reach out to any of those people. All right, just a quick overview of the agenda. So we're going to go over the motivation of why they did this, technical challenges that they kind of thought about and worked through, what the solution overview is, dive in a little bit around the details of the solution that they came up with and walk through those components, then talk about what available solutions we have today along with things that they've implemented in the China Systems Centers lab on how they address these situations today. And then just a couple takeaways to close it out. So as we all know, data, right? Data is growing at an exponential rate. And that's all we see is more and more data, more warehouses. And the graphs on the screen here kind of depict that. And something of interest that they wanted to show up is that core is growing, but at the same time, the amount of storage on the edge is also growing. So that's of concern that we got to think about in the future. All right, I'm assuming a lot of people have seen, or have hopefully seen the Backblaze reports on disk failures. So this report on the screen kind of goes over approximately, I think, 230,000 drives and the failure rates of those drives. So it kind of compares the different models. And there's also another comparison of different drive manufacturers. And it kind of shows you that, depending on what model and what year and whatever you're using, things vary, right? As you can tell from that graph, it's never steady. There's always a variation of what you get and what happens within drives. So as you know, as those failure rates happen, there's some financial recourse, right? We actually have failures, and those failures cause actually money impact, financial impact. So from the graphs, you can see things ranging from a few $1,000 to a few $100,000 to into the millions, right? Depending on how bad those drive failures are, the storage failures are, can be a pretty big impact to the company. So we need to start taking things seriously. How can we stop preventing these failures from happening, and kind of avoid those costly expenses from those drive failures? All right, the next thing I have on here is diversity. So this is talking about the challenges that they kind of thought about when they're looking at this. And as you know, there are many different media types. So we have hard drives, so the spinning disk media, solid state disk, tape, optical disk drives. All these have different challenges and different difficulties you have to kind of take in consideration, right? Because if you think about a solid state drive, there's nothing spinning, nothing to break, right? But you know, there's always other things that could be causing a solid state drive to fail, right? Number of writes, for example. So these are all the different things they had to start thinking about as they started working on this case. Before I move on, I'm kind of curious, the people in the crowd, how many people still use tape or know that you guys have tape in their data centers? There's some people with tape, yeah. I bet you didn't know almost all hyperscalers have tape still with all their cold storage. This is pretty crazy. Next question. How about optical storage? Like a CD or DVDs? What are those? Yeah. So yeah, back in when I don't know, several years ago when I was working for a bank in the United States, we actually, before we had check archives, right, where you just went online and picked out your check, they actually burned onto those CDs check images, and that was the those companies' archives, and they would actually put them in the mail, send them off. And hope they got there and said, "There's your checks, right? There's your archive for your checks. Keep safe hold of them." But things have changed. Now we are keeping all that stuff within the data centers, on drives and tapes and whatever. As I was talking about the different media types, also we got to consider scale, right? As you can kind of see on the screen, there's actually a pretty good number of growth across all those different media types, right? We still have a good growth in tape. I was surprised to see that optical is still there, but it's pretty equal. But there's still a pretty large growth in hard drives, right? Because I think a lot of people are switching to hard drives for archive storage, right? It's easy, swappable, easy to use. So the question is, if you start having failures with your backups, what happens if you have failures with your normal drives? So it's a concern, right? We got to make sure that everything we have and everything that we use is available. Some interesting fact, which I was kind of surprised when I saw this, is 175 zettabytes by 2025 worldwide data. So that's I don't know, I can't even imagine that much data. So I'll ask you guys a question after this, but as I'm going through this list, I want you to think about if this is the same list that you guys would come up with. So as the team kind of sat down and thought about this, they said, okay, what are the factors that impact storage media today, right? And the number one thing that they thought about was environmental factors: temperature, humidity, air quality, power stability, physical vibration, anything that's happening around those environments. Something of interest, so that example of the burn image, right, on that you see the burn hole through this circuit board there. Something I didn't realize is that here in Asia, I'm kind of curious too, this is another question for the audience. They said that they've actually switched away from the system lab from using enterprise drives, which use gold and silver and all these rare minerals, to using copper. Because depending on the air quality, that air quality can actually still be corrosive to some of the materials. So I don't know, have you guys ever heard that before? Raise of hands, I'm curious, trying to keep you guys awake. But that's the first time I've kind of heard that just an environmental factor causing something like that and causing those drives to fail. Next is mechanical failures, right? So as we all know, if you have hard drives, those motors could fail. And then we have media failures. If you have, especially if you have tape, you can get tapes being stuck, grippers being stuck. All these things can be, causing of errors or basically issues with the drives, the tapes themselves. Electrical failures, right? If you think about it, if you have electrical power spikes, other issues where you have power outages, brownouts, all these things can actually impact things even like flash memory. Software errors, those are kind of really hard to detect, right? If you don't really know that you're actually having a bad write until after it happens. Next one is data corruption, right? Viruses, malware, things like that. And the last one, aging issues, right? So just drives just get old over time and start to fail. So I don't know, I thought that was a pretty good list of how complex the problem can be. Oh, actually, yeah. Just to double check, I'm curious. I didn't see anyone raising their hand, but is air quality a concern? Have you guys ever seen that as a big concern? No? Yeah, I was surprised. It's very interesting, because I don't know if it's just because it's depending on the size, and maybe if you don't have air filters and other things like that, but that's kind of an interesting thing to take into consideration. Open appliance, is that what you said? I'm sorry.
Home appliances.
Okay, yeah. Exactly. I think this is probably more of in the edge, I would assume, right? Where you're having the open environments causing impacts. That's very true. I didn't think about that. Thank you very much. All right, known factors. So, and this is kind of going over a list of things just to understand what metrics we have, right, to look at. And I think the number one thing we kind of all agree on, SMART, right? The SMART stats, understanding how that's being monitored. But as you know, SMART is not the same across every model or manufacturer, right? So you can't just take a number and say it's the same thing for everything, right? You have to look and actually see what are all these different values. And it's hard to see, but the chart on the left, and that's all examples of metrics, and it shows up or down arrows, right? If that number should be higher or lower, and if that's an impact, right? If it's saying this number is starting to gradually rise, this could be a possible problem, right? But we can't compare the numbers. Numbers don't mean anything, right? So if we have a rule saying that it's set at 100, that 100's bad, that's probably only specific to that one drive. Storage data performance, right? This is also a key indicator, right? If you're monitoring HPM and you're not monitoring your IOPS or your disk speed, your transfer rate, that could be also a significant indicator, right? But it may not, right? Because who knows, maybe it's just the drive itself is a higher capacity drive, and as you fill it up, maybe it switches from the high speed, single switch transistors to more, triple layer. Next one, environmental and monitoring data. So this is also important, right? Taking in consideration, like I said, the temperatures, the humidity, air quality, all these things need to be taken into consideration. And the last, metadata and maintenance data. So knowing external factors, right, like the backblaze example, understanding which drives fail often and a lot, and also maintenance logs, understanding your internal information about what things fail in my own data centers. All right, known solutions. So the team said, okay, now we have all this information, we know what to collect. What are some ways we can help solve for these items, right? So the first one they thought about, threshold-based, right, rule-based approaches, and that was just kind of referring to the last slide. Can we look at the SMART data and say, yes, let's apply a rule to that? Yes, you could, right, if you knew that it was increasing and maybe set a rule saying if it's increasing over a certain period of time, but that may not really be the best thing, right? It depends. But if you have, specific knowledge, maybe you can apply that knowledge. Next one is statistics-based approaches, using historical information, right? Going back to that idea of going to Blackblaze, looking at how this particular model has always been known to fail in these particular conditions, that may be able to help. And then I think the next best one is learn-based approaches, right? Taking what you have, using machine learning, doing modeling, and basically refeeding that model over and over again until you get better and better and better at predicting those items, right? So using random forest, support vector machines, neural networks. So if you're a data scientist, I think you're probably pretty aware of what options you have out there that you can do with your modeling. Problems and value propositions. So for this one, they're trying to figure out what's the problem? Let's state the problem out loud, right? And how can we solve for it? So as we talked about in the last slide, we wanted to figure out how can we solve for that. And as you can kind of see if you're reading the slide, I don't know if you can see it or not, they're kind of settling on the whole detect, predict anomalies, right? For massive storage, that's the best way to do it. But they want to figure out how to do that. That's not costly or time consuming, right? Because there's so many different dimensions to look at, that's a concern. Data changes at a fast rate, also a concern. There's large scale, things are changing all the time. And we also need to be able to detect this in real time, right? So these are the problems we have to solve for. So what did they come up with? So the novel approach that they decided to work on was, let's do a balance of accuracy, performance, sustainability, and cost, right? By doing what they call active sampling, right? By doing what's called a highly representative sampling data that's highly representative of the high-risk devices, things they know that's concerning, or areas within the data center, maybe external to the data center, that's maybe a high risk. Regular example, right? If it's external and it's sitting in the outside weather, there's environmental conditions. Maybe we should be sampling more on some other environmental statistics so that we can make the right knowledge on that one. Phase-based, this is the idea of reducing the amount of sample that we're gathering and filtering out the noise, right? Just getting what we need to get from the data that we have. And then the last is learning, right? Keeping that learning enabled, because even though you may create a model, most of the time when you create a model, you don't have enough data, right? The data may shift, you may get new models, and all of a sudden you need to go and retrain the model, right? So this solution needs to have some type of retraining built into it. So here's the eye chart for today. So if everyone has the binoculars, pull those binoculars out and start reading. No, I'm actually going to step through each one of these and individually and talk about them. But I think that the key takeaway here, though, is that all these components work together, right, in a seamless approach to create the final solution. So I'm going to pause real quick because I've been talking for a while. All right, and ask the question, and I want you guys to shout it out before I jump to the next piece. So I came up with one, I looked one up. So what's a 5-letter word typed in all capital letters, in English, of course, that can be read the same upside down, then right side up? Any guesses? All capital letters, spelled the same way, upside down as right side up. It's swim. S-W-I-M-E. If you flip it around, spell the same thing. Pretty cool. All right, I got another one. Okay, trying to get you guys awake here. All right, next one is, all right, which fish cost the most? Which fish cost the most? Anyone? It's right, goldfish. Good job. Thank you. Awesome. Right, I just want to try to wake you guys up a little bit. I know we had a long lunch, a long break, so keep it going a little bit here. Awesome. All right, so the next one is the first components. So the first one I have is the active sampler. So we're double-clicking a little bit in the overall diagram that we showed below on the last slide. I apologize. So the whole point of this module, this component, is to capture the data, right? But only data that's highly representative of what we're trying to know, right? And things that are high risk. So the key inputs here are things like the performance statistics, environmental statistics, metadata, and log data, right? Things that we know that could be causing impacts in real time. And this particular output then is sampled, right? We only have a sample coming out of this, not all the data, because that's just too much data to consume. So we take a sample of that data, and sorry, this goes a little double click into it, and then we have the next few components. I apologize. Is looking at the side they have environmental anomaly predictor, right, and that's looking at the environmental anomalies. Next one is performance anomalies, and then a smart anomalies. So the idea is to collect all these things together, and then just get samplings of all those items, and then feeding them into the next component, which is what they're calling failure prediction, the failure prediction module. And the purpose of this one is to predict device failures based on the sampling that's been fed into it. So the input is everything that was sampled before, and the output. The idea of this is not to get an output of like, this is, I analyze it and this is some output. The idea is to be more specific with the output, right, on the condition, right? Put it into buckets. So the buckets that they settled on was one, missing, right? That there's possibly that this drive is known based on these conditions, it's going to disappear. It's going to show up missing. Or it might show up as dead or failing in the future, or it may have expected to have a condition of read-only, right? And the last one is slow, right, which is performance, right? Based on some performance statistics, we're expecting that that's going to be slow. So those are the buckets that kind of get fed out of that particular module. All right, the next one is the benchmark model builder. The purpose of this is to take an input from the other ones, right? But it's more specific around looking at the historical data and other data, for example, benchmark data that's either external or internal, and then working with the models themselves, right? And the idea is overall, we want to create new models as things change. So that's what this particular model, this particular component is all about, is pulling in those historical informations and then outputting models that are more specific to detecting issues with the environment, performance, and smart, and feeding that back into the sampler, if you remember the sampler from the very beginning. And this is the last component, the adaptive scheduler. So the whole reason for this is to figure out how often we should be sampling, and if there needs to be an on-demand schedule of the model. So let's say if we're noticing that we're starting to get some drift on our model, the idea of this is to schedule a rebuild of that model so that, you know, something's not right. So a good example would be, let's say a prediction that something's going to fail, but then nothing happens. You just let it go and you notice nothing ever happened, but something else happens, right? Then you can help do the analysis and change the models based on the output of this. All right, so that. Oh, this is last slide. This is like a double clicking a little bit more into the scheduler. So there's three components: the evaluator, policy determination, the scheduler. So the evaluator looks at the data and the deltas between the data, right, to help that determination. Then there's the policy determination to see if we need to make changes to the schedule of the policies. And the last one is how often should those schedules be changed, how the sampling should happen. All right, so the next couple slides kind of talks about where this was implemented and where they tried it out within the China Systems Center. So the China Systems Center is a pretty good size environment. And if you were in the last presentation we had yesterday, there was a video that actually went over showing all the components and assets within that environment. Oop, not sure what that happened. It allows, basically what the China Systems Center does is allows you to come visit them. They do demos. You can do hands-on training and trials and errors of different things that they have within the lab. So it's kind of a way you can get, you know, customers in to try different things out within their environment. They have, with the environment they have set up, they have mainframes, of course, this is IBM. We have power systems and x86 systems. We also have storage. So the storage that they focused on was some flash storage, some hard drive storage, and also, I believe they have some tape storage, the TS 4500s. And this is an example of what we're doing overall in most of all the labs within IBM. We're moving to what we're calling a full stack sustainable optimization platform. So on the left-hand side, that's the full stack, right? Looking at the full stack for observability, and then moving to the right is all the different components that we kind of want to optimize for. But of course, we're just going to look at the storage perspective, not everything else. But still, the storage perspective should be from the full stack, right? Because something that happens in the building or outside the building, or if that drives somewhere else, can impact it, right? It could even be something at the very top, right? Something the application is doing can impact those drives too. So we should be looking at the full stack. Don't worry about this. Like I said, I'll get the PDF out after the presentation. You guys can take a look at this. This is the kind of an architecture of how things are put together and monitored. All right, and then the next few slides I have kind of goes into the personas. So the idea is we want to monitor, right? But we want to monitor based on and show details and observability based on the personas of who wants to look at it. So this example is more, I think, geared towards maybe the SRE, maybe data center people. It's maybe hard to read, but it shows information on what's going with the sensors in the environments, so what the power usage is, real-time environmental matrix monitoring over time for different systems. It's basically just an overview of what's kind of happening. But the overall idea, though, is, and I'll go through them here in a minute, all these different things I'm going to show you, it's based on a persona. So like this persona may be, an SRE data center. But then we also have personas for sustainability people, right? And we also have personas for maybe an application or a database person, right? There's all these different personas, and we have to kind of put things in perspective. All right, so the next thing that we have within the labs is, of course, we'll have APM, application performance monitoring. In our particular case, we're using Instana. And within Instana, you can look at a lot of the application performance and drill down within the storage and look at what's happening with your storage subsystems, how they're performing or not performing well or not performing well, and what's happening with them. So this all kind of feeds into that statistics modeling and sampling. This is an example of the smart monitoring that's happening during the POC. This is just showing an example of, the smart data over time and how that's changing and how that's being used to model level predictions in the future. This one is specific to storage optimization. So it's a product called Thermonomic, which allows full stack topology view of what you're looking at, and you can kind of drill down to the storage level and see what's happening with your storage and figuring out if you're using too much storage or not enough storage, if there's a performance issue or not. And the idea would be, to take what we have with the performance issues and anomalies and put that anomaly detection within this view. Next one is assets. So if you have a whole bunch of assets storing, if you have assets, right, and those assets are storage, the idea of this is looking at that as an overall asset and how we can improve it. So EIM, right, Enterprise Asset Management, and then taking that asset management, adding IoT information, that sensor data reading in, right? And then the next evolution from just getting like sensor data is taking that sensor data and understanding the health and predictability of it. And then the very last, the very top is assist, right? Helping out your senior SREs, maybe fix something, repair a drive, whatever have you. This is an example of storage health, device health detection, failure detection. If you look, it might be kind of hard to see, but you can see that there's, at the very far right, I should say, on the screen, is failures. And then depending on the statistics that are being gathered, the modeling in the background is happening continuously, and if there's a failure detection, alerts generated, a prompt tickets generated, and you come to this page to see what the overall health is, the first view, right? So this could be most likely an IT person, right, looking, understanding, trying what's going on. Maybe it's being referred to if the alert's saying there's a environmental impact issue, right? It's just overheating. This would be directed most likely to the data center manager or someone within the data center. Not sure why it's jumping, I apologize. All right, and then this one is an example of persona of being able to drill down more specifically and looking at the power usage of all these different drives and seeing the variation and determining if maybe something particularly happened that particular day, and maybe someone was swapping out a drive, or maybe there was something was changing in PDU, who knows, right? Something was happening, and you can detect that and say, okay, I know what happened at that time. It really is not going to cause, not a sign of a drive or storage system failure. All right, and the last one is just an example of looking all the way up to even people outside, right, engineering and sustainability, taking things and being able to show that, hey, based on changes in the environment, we can see PUE changes and how that's affecting our environmental and sustainability. All right, the last slide, takeaways. So as you hopefully kind of gathered from the presentation today, health and storage devices are really vital, right? We need to make sure that we maintain them. The overall idea, though, is that we need to take a full stack approach, right? Look at it holistically from start to end, understand everything, right? Because if you're just looking at a subset of data like the smart data, that's just not enough. And also, how can we, by looking at all that, that's a lot of data, right? So how can we balance the performance, accuracy, sustainability, and cost, and that's what hopefully you kind of gathered from what I was talking about before, and what they've kind of filed for a patent on is all these different components, how they can work together to kind of, show you failures, but by looking just at a sample of that data. And one last slide, I do want to show the people, if I can keep it up. These are the people that were all actually working on it with a team, and so I wanted, if they're watching the video, thank you guys for doing this. This is amazing. Great shout out to all those people at IBM. So I'll open it up for questions. Thanks.